In this video, we're going to look at the concepts of buoyancy and stability. And first, we're going to look at the buoyant force on a submerged object. So we'll draw a submerged object here. Here is our water level, and we're going to draw a submerged box here. Now, the height of this box is A, and the upper surface is submerged to a distance of h1, and the lower surface of this box is submerged to a distance of h2, or to a depth of h2. Now, if we're considering the forces on this submerged object, we know right away that there is a pressure force acting on this upper surface. This is simply a horizontal plane. And so we have a pressure acting on that surface, which we'll call F1. And we know that F1 is equal to gamma H1A. It's just as if the surface is at the bottom of a swimming pool. It's just an arbitrary horizontal surface, and so we know that the pressure there is rho g H1, or gamma H1, and then we multiply that pressure by the area A, and that gives us our force. And I should mention that this object is a cube with face area A. So all of the dimensions have an area of A. So the force on this upper surface is gamma H1A. And similarly, we have a similar force, a similar but larger force on the bottom surface, and we'll call this F2. And we can write F2 as gamma H2A. So we have F1 is gamma H1A, and F2 is gamma H2A. And we define the buoyant force, F sub B, as equal to this difference, F2 minus F1. And we can plug in these formulas that we've just derived for F2 and F1. So gamma H2A minus gamma H1A. And what we find is that F sub B is equal to gamma times A times this difference, H2 minus H1. And just to remind you that gamma here is the specific weight of the fluid. We have come across that property several times before. But also, A times H2 minus H1 has a special meaning here. This turns out to be the volume of this cube. We have the area of the cube multiplied by H2 minus H1, which is the height, and that gives us the volume. So we can generalize our equation here for the buoyant force as equal to gamma times V. And here I'm writing the V with a strike through to indicate the volume of the body. So your buoyant force is simply equal to the specific weight of the fluid multiplied by the volume of the body. Now, we have a couple notes here about the buoyant force. The buoyant force is the force of the fluid on the body. It has a magnitude equal to the weight of the displaced fluid and is directed upwards. Right, because the volume of the body is the volume of the displaced fluid multiplied by gamma, which is the specific weight of water. And so the magnitude of the buoyant force is equal to the weight of the displaced fluid. And this is directed upwards. Now, we haven't talked about the weight of the fluid. And the weight of the fluid is important, we haven't talked about the weight of the object. And it's this balance between the buoyant force, F sub B, and the weight, W, which determines if the object floats or sinks. So if F sub B is greater than the weight, then the object will float, and vice versa as well. And then one last note about this, the buoyant force F sub B passes through the centroid of the displaced volume. And this has a special name, which is called the center of buoyancy. So that is the buoyant force. It's simply gamma times the volume of the body directed upwards. And the balance of this buoyant force and the weight determines if the object will float or sink. So moving on to the second and related concept, we're going to talk briefly about stability. And so how do we define stability in this context? So a body is in stable equilibrium if, when that body is slightly perturbed, it returns to its original position. And in contrast, a body is unstable if, when perturbed, again a slight perturbation, it doesn't return. And we can illustrate this potentially by drawing something like a bowl. So let's say we have a bowl right here, and we have a ping pong ball which is in the bottom of that bowl. And we'll draw it in blue. So if we perturb the position of this ball by moving it slightly up the wall or up the edge of the bowl, this will, when released, return to its original position. And so this is a stable system. Now then, what happens if we turn this ball up, if we turn this bowl upside down? So now if we have a perfectly balanced ping pong ball on the top of this bowl, and we slightly perturb it to this position, what's going to happen to it? It is going to continue rolling down the side of this bowl. And so this is an unstable configuration. Now, what does this have to do with buoyancy? So we can apply it in the following way. Body is stable if its center of gravity is located below the center of buoyancy. And unstable if otherwise. And we can illustrate this with a couple of drawings. So we're going to draw a water surface right here. And this is going to be our stable configuration here on the left. And so we can imagine that we have some sort of a prolate spheroid sort of shape, this elongated shape like this. And maybe it has some sort of weight. It's weighted at the bottom. So in this case, the buoyant force is going to act here. It's going to act through the centroid of the displaced volume. So this is going to be the location of our buoyant force right here, right in the centroid. But because we have this weight at the bottom, we have this weight acting down here from this location. And so in this case, if we perturb this shape like this, such that, again, we still have the weight at the bottom, when we do this, we have again, we have a force, the buoyant force acting upwards here, and we have the weight force acting here. In this case, this creates a restoring couple. We have this moment that acts to return this submerged object to its original position. And so this would be a stable configuration. Now, alternatively, if we can illustrate an unstable configuration by turning this object upside down in the water. So again, we have the same object. Now the weight is located at the top. So now we have this weight acting through this point right here, and we have the buoyant force acting through, again, the centroid. This is F sub B. So now if we perturb this object and turn it by some angle, now we have, again, the weight still acting downwards from this location. We have the buoyant force acting still through the centroid. But now we have a couple that's acting to overturn this object. So this is an overturning couple. And so this is how we can apply the concepts of stability and instability to submerged objects. Now this is for if the objects are completely submerged. It gets a bit more complicated. A floating object that is only partially submerged. This is more complicated for floating bodies the reason for that is because the location center of buoyancy may change as that object rotates or as it's disturbed. And so you could sort of imagine how that might be if you have a some sort of vessel sort of floating at the surface. So that part of the object is above the water, part of it's below the water, and so you can see how in some cases that center of buoyancy may shift as the object rotates or moves in the water. So that is an illustration of, or that is our look at buoyant forces on a submerged object and on stability.